Hello, everybody. Good morning for those in Brazil, in Belém. Good afternoon for those in Europe. So it's an immense pleasure for me to welcome you all to this special lecture inserted in the 6th Amazonian Symposium on Physics. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed in the end, unless otherwise requested by Professor Reinhard Genzel. The question can be asked using the chat. And if you are following by YouTube, you can write it down in YouTube and I'll read your question for you. Today, we will have a great honor to listen to Professor Reinhard Genzel, who was awarded with the 2020 Nobel Prize in Physics, together with Andrea Ghez and Roger Penrose. Professor Reinhard Genzel was born in Germany. He received his PhD in physics and astronomy in 1978 at the University of Bonn, with a thesis in radio astronomy prepared at the Max Planck Institute for Radio Astronomy at Bonn. He's an honorary professor of physics at the Ludwig Maximilian University in Munich, and at the University of California in Berkeley, he was a full professor at the Department of Physics and Astronomy from 1998 to 2016. In 2017, he became professor of the graduate school at UC Berkeley. Our special guest is a fellow of the Royal Society and is presently director of the Max Planck Institute for Extraterrestrial Physics in Munich, in Germany. Apart from the Nobel Prize in Physics, Professor Genzel research has been honored with various prizes and recognitions, including the Otto Hahn Medal and Balzan, Shaw, Crawford, Tycho Brahe, and Harvey Prize. Experimental studies of black holes, status, and prospects is what Professor Genzel will tell us about today, and I should not make you wait longer to listen to him. Professor Genzel, thank you very much once again for having accepted our invitation, and from this moment on, the audience is yours. Thank you.
Thank you, Louis. Hello, everyone. Hello from Germany and from black holes. So what I want to do today is to tell you about a rather impressive progress which has occurred over the last about 30 years on truly physics experimental evidence about black holes, whether they exist or not, and then learning about their cosmic evolution. Now, I assume that most of you are experts in black holes anyhow, since black holes are sort of the favorite topic of science fiction, and Kip Thorne has participated in making the movie Interstellar and made black holes even more famous. But this talk, in that sense, is a little different. It really deals with hardcore physics and what we actually now know about these objects. Now, you will perhaps know that, of course, the issue of black holes came pretty much immediately as soon as Albert Einstein announced his theory of general relativity in 1915. 1 year later, the man there in top, Carl Schwarzschild, found the first solution of the equations in a spherically symmetric situation. And this solution already had the black hole issue in it. Why? What's so special? The special thing is, compared to Newton's description of gravity, is that in Einstein's theory, gravity is actually not just a force, but it's a disturbance of what we call space-time, which propagates through space and time with the maximum speed of communication, and that's the speed of light. We now can actually, with experiments, test that indeed, but at that time that was sort of a prediction of the theory, and light, or photons, if you like, also have to adhere to this, since there's an equivalence of mass and energy in Einstein's equations, which means that effectively light also sees perturbations in space-time. In other words, if you think about the analogy of a rocket lifting off from the Earth, And we know nowadays, everyone, even children, know that the rocket has to have a minimum speed in order to get away from Earth. And this speed depends on the mass of the Earth, but also the size of the Earth. And the larger the mass and the smaller the size, the larger the velocity of that rocket. So if you go to the extreme case of a very compact object, like for instance, make the sun 3 kilometers in size in your mind, then all of a sudden a rocket would have to fly away from the surface of that object with the speed of light or greater, and that is not possible. So that's immediately, so to speak, a prediction that there is a characteristic radius, we call that the event horizon, within which nothing can escape, no bodies and no light, and nothing can go faster than light. Now, this is, of course, a very special situation, spherical symmetry. So it took a while for the theorists to explore this. In 1963, the man on the lower right there, Roy Kerr, found a second solution for a axisymmetric spacetime, which would then describe a rotating black hole. And so given that theory, the so-called Kerr spacetime predicts that a black hole can only have two properties. One is the mass, and the other one is the spin. Everything else follows automatically from that. But then the question many physicists start asking at that time is, well, okay, that's theory and mathematics and so forth, but could these objects really be realized in nature? Because in order to press, if you like, if you bring a material to such a small size as a black hole of the size of the sun would truly be very, very small objects of only a few kilometers in size. So the question is that perhaps not realistic. So the man in the lower center, Roger Penrose, showed no, if there's a critical curvature of space-time above which, indeed, you get into these solutions we what called black holes. So nothing can escape from black holes. Is that right? Well, the man on the upper right, Stephen Hawking, was one of the first ones who thought, well, no, wait a second, what about on small scales? On small scales, the theory says that all of the mass or the energy of the black hole should reside at its center in a infinitely dense singularity. But we know in physics that singularities is a thing which depends a little bit on what resolution you have with your testing apparatus. So Hawking said, well, if he would devise a quantum theory of general relativity, which we don't have, then there would be things like the uncertainty principle of Heisenberg. And the uncertainty principle of Heisenberg allow you to have tunneling of particles or light through a barrier which it otherwise cannot go through. And that's the same as saying light can escape, although in very small quantities, from a black hole. So that's Hawking radiation. We have not seen that yet. And it will be extremely difficult, if not impossible to see it. So that's general relativity in a few minutes. Now, around 1963, in fact, the astronomers began hunting for black holes as well. And that started with the discovery of objects which are very, very faint, point-like in nature. You see there a picture, looks like a star, a faint star. There's a little bit of some gunk on the upper left there. And when Martin Schmidt, the one on the lower left, took the big Palomar telescope and took a spectrum of this object, he found spectral lines which all were very well known, but their wavelengths were all shifted relative to the laboratory on Earth by 15%. Now that is unusual. How could that be? Well, of course, the expansion of the universe was known by then already several 10 years. And so many people said, well, maybe that means that this object we are looking at is really far away from us. And therefore, because of in an expanding universe, the further something is away from you, the more redshifted it is. So in this explanation, this object there is actually at 3 billion light years away from us. An incredible number for that time. Now, within a decade, hundreds and up to now millions of such quasars, quasi-stellar radio sources, have been discovered. Very rare, but very, very far away. And because they are so far away, what looks like a little teeny speck of light is actually very powerful in terms of the actual emission of radiation. No, and also very hard radiation, X-rays, gamma rays, and also particles. And this little gurk there, which I pointed out, is actually a jet of highly ionized gas, which is expanding away at almost the speed of light from the central quasar. So the picture we have now, which was developed by a number of theorists like Lyndon Bell in the middle down there and Martin Rees and others, is that quasars are massive black holes, very, very massive black holes, 1 million to 10 billion solar masses, onto which material falls and falls in because of the gravity of the black hole. And because that material typically has some amount of angular momentum, it doesn't fall straight in, but falls into sort of a disk-like configuration. And through magnetic friction, it can then release its angular momentum and slowly fall inward. And in this process, near the event horizon, before it disappears, it emits an enormous amount of energy because mc squared is such a large number. So up to 40% mc squared can be emitted before a particle disappears behind a maximum rotating black hole. So that's the theoretical picture at in around 1971. But how to prove that? If it's black, how would you see it? How do you see it? Well, through gravity. Think of the planets around the sun. Even if the sun wouldn't shine, you would still be able to measure the mass of the sun by observing the motions of the planets orbiting around it. They're bound to the sun, and you can use the laws of gravity to determine then the mass of the sun. So the similar picture we might think of in terms of these quasars. If we could make measurements of gas or stars orbiting these objects, well, maybe we could then prove that they indeed are 1 million to billion solar mass objects. That's at least what Lyndon Bell and Rees proposed in a paper in 1971. That was sort of the signal, if you like, where the hunt started. And it took really 40 years until the hunt was successful. One way to do this is what we did, we meaning my group and I, and also Andrea Ghez and her group at UCLA, is to measure the next nearest galactic center, hoping that a quasar is a very distant object, but maybe black holes are common. It's just that only very few of them have so much accretion, like in quasars, that they are so bright. Maybe if you have little accretion, you could say that black holes are actually very common, maybe even in our galactic center. So that's is what we have done, and I will tell you what emerged from this. A second way, which came about, started around the same time. In the 70s, a number of people started to want to measure the gravitational waves. So for instance, if you have two black holes orbiting each other, then they lose energy because of the emission of gravitational waves, and always come closer and closer together, and finally they merge to a single black hole. That's that picture you see below. You see initially there is a wave due to the orbital motion, and then the wave becomes larger in amplitude as the objects come closer to each other. But in the end, the frequency gets higher because, of course, now the motions get faster. But in the end, everything is quiet because the two objects merge into one. So that's the second way, and also that took 40 years. And finally, another way to hunt black holes turns out to be photons. Photons, by using the fact that, as I explained, gravitation bends space-time, and photons sees that bending. So if you shine light on a black hole from the backside and look at it from the front side, you will see a characteristic shadow profile, which you see there on the right side. So I'll tell you more about these three techniques. It's remarkable that within a relatively short period of time, after, however, 40 years of hard work, hard experimental work, ever more improving equipment and so forth, we are where we want to be. Now, of course, the critical thing is angular resolution. And if you take a picture with a telescope, then of course the Earth's atmosphere on the ground distorts that picture such that you do not get what you would like to have, which is the diffraction limit of resolution. The diffraction limit of resolution in angle on the sky being the ratio of the wavelength to the size of your telescope, lambda over d, which for a big telescope, an 8-meter telescope, is only a few tens of a milliarc seconds. But that you don't get unless you basically flatten the wavefronts through adaptive optics. And that's a technique which got developed in these years, such that we can now turn our big telescopes truly into diffraction limited devices. Yeah, we can even go further, which is we can combine the light from several telescopes and go to large baselines for which you would not be able to build a single telescope. And that's called interferometry, first device in the radio band. And in fact, it was Michelson, a famous Michelson, who in the 1920s used the Mount Wilson telescope, which you see in front of you, to mount at the top of it this bar with deflecting prisms such that the outer parts of this bar have a separation much greater than the size of the telescope. And by bringing in the light together, you can then interfere the light from the distant star and begin to resolve it. And you see these stripes of positive and destructive and constructive interference. So the interferometry allows us to get resolutions bigger than that of a single telescope. In fact, down below is the instrument we are using now, which is in Chile, the 4 8-meter telescopes of the European Southern Observatory. So we have developed over the last 15 years an instrument called Gravity, where we combine the light of these 4 telescopes to then achieve the equivalent of a telescope of 150 meters in diameter. Terrific. The resolution is only a few milliarc seconds. The radio astronomers have pushed that even further by at radio wavelength and put telescopes all over the globe. The record holder is the so-called Event Horizon Very Long Baseline Interferometry Telescope, where the entire globe is covered with a few telescopes, and you observe at a relatively short wavelength, so that lambda over d, in that case, becomes only a few tens of microarc seconds. That one, in fact, comes very close to being able to directly resolve, the shadow of a black hole, and I'll show you the result. And finally, the the gravitational wave experiments are also the same kind of a technique, interferometry and two-armed interferometry, Michelson interferometers, where you combine then the light and measure the distortions between the beams in the two arms, and that allows you to get extremely high resolution. So it's really funny in a way that after all this time, it's been these three techniques, mostly building up on Michelson's work or Young's work, that allowed us now to hunt down on black holes in a truly experimental fashion. Of course, you could say, well, why do we do it like the movie Interstellar? Just travel close to a black hole and make direct measurements. Well, that's not very practical, because most of these objects are so far away that we would obviously, even with the fastest rockets, would never get there. Okay, so now we want to hunt these black holes, and we had already a first candidate, which I described to you, this quasar, which I showed you earlier. So that gave us a hint that if you have a black hole in a galaxy which is accreting, then you see radiation phenomena, X-rays, hard X-rays, you see these jets and so forth. So the astronomy community started hunting black holes by looking for what's known as active galactic nuclei. There you see the definition you find in Wikipedia. An active galactic nucleus is a compact region at the center of a galaxy, and the non-stellar radiation from an AGN is theorized to result from the accretion of matter by a supermassive black hole at the center of its host galaxy. So that's been sort of the assumption, and on the right you have sort of a schematic how this would work. You have in the center a black hole, then you have your accretion disk of material which is spiraling inwards, and then the black hole starts radiating and also emitting these jets. So from this qualitative point of view, by the mid-'80s, I would say, maybe the early '90s, most astronomers were pretty convinced that these black holes indeed existed, and there were various approximate measurements to get at the masses of the black holes. And so from that we've learned that black holes are common. Almost every galaxy, including our own, has a black hole. Very few active, like quasars. There are a whole range of activity levels down to the most boring one, which is the center of our own Milky Way. But is this really truly the kind of proof which we require as physicists to believe that these black holes have been discovered through these AGNs? And the answer is no. And so really to go deeper, you have to talk to the theoretical colleagues who say, no, wait a second, there could be other configurations which look like compact concentrations of matter, space-time, that are, extremely interesting, but not black holes. Perhaps the most likely would be so-called boson stars, or objects which are made out of neutral fermions, fermion balls. And so they have a certain size. We know that from the neutron stars, right? If you make the pressure high enough so that the protons press together, then the protons turn into neutrons, and you have a stable object which is very, very compact, a neutron star, only a kilometer or two in diameter. So maybe that's what it is. It's not a black hole. It's other things. And indeed, there's a whole list of what people have talked about: gravitar stars, fuzz balls, etc., etc. I don't want to bother you with all these names. And the theoretical colleagues are very, very inventive to find ever more ideas of how this could be. So these objects are bigger than the event horizon. Okay, and so while on this diagram on the right, a black hole is way to the left at 0 in this parameter of compactness, defined to be, as you see in the formula, the difference between 1 and the situation at the spherically symmetric black hole. 2gm over c squared is the size of the event horizon. So then if the r, the size, is equal to the event horizon, well, then you have a black hole. So how far away are these objects from being black holes? Well, they can be quite far away. As you see at the bottom there, some of these objects, these boson stars, etc., can be as large as 2, 3, 4, 5, 10 times the event horizon size. So the job which we as experimentalists have is to make spatially resolved measurements of the dynamics of space-time around suspected black holes and show that they indeed cannot be one of these pretenders, but really truly are black holes. And that's why, of course, given the size of the event horizon being so small, it's really the challenge. Let's start with the galactic center. We know since a long time that the center of our galaxy is a very dense star cluster. Here's an infrared picture. You cannot in the optical see the galactic center because of dust in the foreground, but there's a very dense star cluster. You see very bright stars and also different colors, different temperatures of stars. And there's a little marker of 0.5 light years. So this is really the very, very center of our galaxy. There is also this red circle. That's where there is a compact radio source, which the radio astronomers discovered in the 1970s. And so many people said, well, okay, so there's a dense star cluster, and then there's a very compact radio source. Maybe that's a black hole. So this object, which we call Sag star, is, so to speak, our candidate. Is that a black hole? Well, if you take big telescopes like I described to you, like the Keck telescopes or the VLT of ESO, or then the interferometric expansion of that, you can resolve this innermost yellow square there on the left side, which is the innermost, few tenths of a light year. That is, however, still 100,000 times or more the event horizon of a million solar mass black hole. So it's not anywhere close to the event horizon. Nevertheless, when you take a picture with normal telescopes, that's what you get to see. Where the radio source is, the red circle, there's not much, a little smeared out stuff. But there's some very bright stars in the vicinity. And so when the theorists saw that emerge, they sort of said, oh, well, that doesn't look like a black hole. Where's the accretion ones? And then why is it not bright there? Well, we need more resolution. And so the adaptive optics image, the equivalent adaptive optics image with an 8-meter telescope of the same region is here, much higher resolution. You see the big stars are much more compact in size, apparently. But what about at the radio source? Well, not much there. Or, well, if we look deeper, which we can with these with adaptive optics, there is some emission there. Not much, but there is some emission there, plus other stars. And so the idea which we had, and also Andrea, I guess, was to go ahead and see whether we can measure the positions of those stars, and over time the changes in position, and therefore the velocities and the motions, and if perhaps one is lucky, even the orbits. However, that takes a long time. You have to have a lot of persistence, even with the best measurement techniques, because the motions of these objects are milliarc seconds per year or less. You have to measure for 10 to 30 years. But then with the interferometry, we can jump another factor of 20 inwards. And look what we get to see. We get to see Sergei star there, the center, right, a infrared source associated with the red circle. So there is some emission from the black hole candidate. And in the very vicinity on this now scale of only a few thousand, not 100,000, but a few thousand Schwarzschild radii, we see stars moving very fast. These two stars there move with typically, 6, 7, 8,000 kilometers per second. And you will see in a second that we can not only measure the motions, we can measure actually the orbits. So there we are. That's the status after, 30 plus years of measurement. On the left side, sort of on a bigger picture, Sergei star is the red cross, and then you see the orbits of several of those stars, highly elliptical orbits, actually, very unusual, no circular orbits. But the stars come close to Sergei star, down to scales of about 100 astronomical units. So that's solar system scales, and that's why they move so fast. One of them, the best one, in fact, is shown on the right side there. You see the orbit again. In the bottom, this black circle dot, that's Sergei star. And you see that when the star is near that point there, the Perrier point, it is only about 15 light hours away from the black hole. 15 light hours is about 3 times the orbital radius of the planet Neptune. So really remarkable. But that's only, of course, for a few months, then it goes back out. And then 16 years later, it comes again. So that's when we, in fact, saw this first Perry in 2002. So did Andrea Ghez. And then we said, well, wait a second. The next time it'll be there in 2018. That's when we want to measure, not still better. And still better means either a bigger telescope or interferometry. So that's where we had the idea to do the impossible, namely to develop sensitive optical interferometry. And then in the bottom, you can see what happened in 2018. The star moved at 100 AU by the black hole with 7,600 kilometers per second. When we could measure the positions from night to night, these different red dots there. We can also measure the Doppler motions on the top right due to the Doppler effect in spectral lines. So we can measure the full space coordinates of the star, and therefore then derive the 3-dimensional orbit. And with that, we can, and the Andrea Ghez group as well, measure very precisely the central mass, 4.3 million solar masses, to sub% accuracy, and also the distance to the galactic center with very, very high accuracy. So that's as you will see, that's extremely important, because now we have a very clear and absolutely high quality measurement rod to which we can compare other measurements, and we can test the first time near a black hole general relativity itself. For instance, the so-called gravitational redshift. If a star moves near such a heavy mass, such a black hole, then the light it emits has to escape from the deep potential, and it gets redshifted. In the case of the star S2, the redshift is about 200 kilometers per second. So if Newton is the case, then this shift is 0 at all times. If general relativity is correct, the red curve applies, and you can see that the measurements we've made over these years really confirm clearly, yes, general relativity is dictating the space-time on that scale. The next one is the fact that in Newton, if you have a star or planet orbiting another star and nothing else is around, it changes its orbit not. It stays in the same, say, elliptical orbits for all times. Not so in general relativity. In general relativity, the orbit of the star precesses. It precesses in its plane every turn in prograde fashion, depending on how close it comes to the center. And it also precesses around the spin axis of the black hole if there's a spin. Now the same residual curve now is seen on the right side. If you only have Newton, well then nothing happens and the residual stays zero, zero at all times. General relativity predicts this loopy structure. That's the precession. And the measurements we've made with gravity are the blue points. And you can see that clearly looks like general relativity. Okay, tick off number 2. But the orbit of those stars is still 1,000 times Schwarzschild radii. To really be sure that we are dealing with a black hole, we would like to get closer. And there's 2 ways of doing this. Once, as you will see next, through photons or through hot gas. And indeed, every few days, the galactic center emits a flare of a few hours, which turns out to be hot synchrotron emitting million degree gas. And we can measure its motion during the flare. And the motion is sort of a clockwise motion on a scale of about 4 Schwarzschild radii, with a velocity of 3/10 of the velocity of speed of light. And I come back to this in a second. That allows us, if this is indeed virial motion, then that allows us to measure a mass on the scale of the event horizon. Okay, I mentioned already the idea with the photons. So if you have a light source behind the black hole there on the left side, and you look at the photons coming at you, then of course in normal classical geometry, you would expect that there be a dark spot around the black hole. But general relativity says that also photons further away get spent, and some of them never make it to us. So there's going to be a ring around the dark spot. And the ring can be calculated, the size of the ring can be calculated from the mass of the black hole. And since we know the mass of the black hole and the distance, to sub% accuracy, we can predict the size of that ring to be 50 microarc seconds, 51 microarc seconds. And sure enough, that's what our colleagues from the Event Horizon team have published 2 years ago. And so this is a fantastic corollary proof that indeed the mass, which you've seen at 1,000 Schwarzschild radii from the photon, from the stars, is also contained on a scale of only 5 Schwarzschild radii or so. So the mass is still 4 million solar masses, although the accuracy at this point is by far not as great as the accuracy on the stellar measurements. In fact, a theoretical argument can be made if you look at the very center that the faintness of the emission there can be used to make I would say, halfway convincing argument that there is absence of a surface. So that is what you would have if there indeed is an event horizon. So after 40 years, if you plot what we've done, and Andrea and others, plot the enclosed mass as a function of distance from Sergei star, where you notice these are logarithmic units. Look at the top, that's in gravitational radii, half a Schwarzschild radius. You can see that when we started, we were in the top right corner. we were seeing that the mass is extended on large scales, goes up, but then stays constant all the way in to the nearest stars, S2 and these others, which I've shown you. So that is consistent with a black hole, but must it be a black hole? And the answer is no, because you could think of a ball of fermions of 50 kiloelectron volts. Well, they would just have a central core of that size. So in fact, that argument has been made. But then with the measurements of the flares and the size of the EHT shadow, I would say it's going to be very hard to defend any kind of a non-black hole nature. Nevertheless, people are certainly trying to do this. This is the nature of physics. One would have to still be surer of the numbers, and of course, the measurements can still be improved. But I would say the case is pretty tight. And if you want to have now a non-black hole solution that is as small as 10 Schwarzschild radii, okay, so that's what these measurement points are, then the fermion would have to have a mass of about 540 kiloelectron volts in the so-called Oppenheimer-Volkoff limit, which you can calculate. So that's the equivalent of the neutron star solution. And however, if the mass is just a little bigger, then the size is a little smaller, then basically there has to be gravitational collapse. So I would say, while we cannot completely exclude the argument that this must be a black hole, it's very, very likely. Does it have spin? We don't know. We still have to measure, and that's one of the goals we have over the next years. And does general relativity truly still works in this innermost region? Well, that has to be done. But we've come far along in 40 years. Now, I told you earlier about the distant massive black holes, the quasars. And until recently, these could not be observed with spatially resolved measurements very much. The picture there is you have the black hole in the center there, this black spot surrounded by the accretion disk, which we discussed. And surrounding that is a cloud of ionized gas, the so-called broadline region, which one can see in optical ultraviolet emission lines as wide wings. And in fact, a way to measure the masses is if this emission is variable, you get an impression of the size of the broadline region. From the velocities, you get an impression of the motion in velocity, and that then can be combined to measure a sort of an approximate mass of the black hole. That's not very accurate, but that is what could be done and has been done on thousands of objects in the last 25 years. But now, actually, with gravity, that interferometric device, we can go one step further. We can actually resolve the broadline region in external galaxies, and in fact, all the way up to redshift 4. Here is a quasar, a very powerful quasar at redshift 2.3. So that's an object which we observe at about 10 gigayears in the past. On the left side, the line is H alpha. You see these broad wings. That's the broad line emission. And then with the interferometer, we can observe the positions of every little one of these wing slabs and plot the phase which we derive, the interferometric phase on the right side. And that's a measure of the separation. And you can see that it is an S shape. The blue side is positive in phase, and the red side is negative in phase. And that is what you would get if you have, like, down below, a rotating broadline region. size is very small, only 40 microarcseconds, and from now we can measure a fairly accurate black hole mass. So that's sort of the future opening up, because we would like to now to measure accurate masses with this technique. To the earliest times, black holes have been sighted, and the James Webb Telescope is bringing one record after the next to show us that black holes already existed at redshift around 10. We don't understand how that will be. I'll come back to this at the end of the talk. Let me say just again on the gravitational waves, there it's not about massive black holes, but about stellar black holes for the ground-based interferometers. As we come to later space-based interferometers, then one can also do supermassive black holes. But as I have shown to you already, this measurement in 2015 was a spectacular first indication that you can measure two black holes of 30 and 40 solar masses, emerging to a 60 solar mass final stellar black hole. If you know something about stellar black holes, you might find one thing a little odd, which is the numbers you would have expected are 10 solar mass plus 10 solar mass, making 20. So this objects, already the initial objects are fairly high in mass, and the LIGO interferometer and the combination of LIGO with Virgo, etc., are finding more and more fairly heavy stellar mass black holes, and that's a puzzle. Is it that stellar black holes, once they have merge again, or do they have accretion onto it like quasars so that they grow? We don't know yet. Something which surely we want to do in the future. Okay, let me now go over to the issue of evolution. What we now know is, as I mentioned, if you measure the black hole mass in the vertical axis in logarithmic units in galaxies versus the galaxy mass, so let's take the central part of it, the bulge mass, then one finds that there is approximately a linear relationship. Pretty much scattery, but still pretty much a linear relationship. About 0.3% in all galaxies of the central stellar mass is in the black hole. Now these galaxies there, which you see there, all have different ages, yet this ratio seems to be pretty constant, at least to modest redshifts. And so this tells us that this correlation can only be because of the evolution. And indeed, if we look at the star formation activity in blue on the one hand, and the quasar densities on the other hand in red, as a function of time after the Big Bang, then we are now to the right, where there's very little activity, very little star formation activity, very little quasar activity. But you see, about 10 gigayears ago, a few billion years after the Big Bang, there was a maximum of star formation activity in galaxies, as well as quasar activity. And you can see that they are sort of approximately have the same evolution. We call that co-evolution. And the picture is that in order to bring a material into a black hole, it has to come from very large scales, intergalactic medium, and then it falls first into the galaxy, and there it can form stars, or then through removal of angular momentum, it can then also fall into the central black hole, which then grows. So if you have a lot of accretion from the intergalactic medium, well, then you have a fast growth. If you have little accretion, well, you won't grow very much. And so, at least qualitatively, that seems to do a pretty good job in explaining these findings of a approximately linear correlation and this sort of peak of cosmic star formation rate. But that one with the James Webb is really puzzling. namely a pretty bright black hole source at redshift 13. Because it turns out that when you want to understand how black hole growth occurs, then of course the luminosity of the quasar is proportional to the accretion rate, m dot c squared, times an efficiency factor, eta. And the maximum, however, luminosity you would think you can allow for is when the accretion rate is so fast that the photon pressure, which emerges from the innermost region, then pushes on the infalling material. So we then call that an Eddington limit. So the mass growth, dm by m, is this efficiency factor times the ratio of L over the Eddington rate in units of a characteristic time scale, which is given by all these numbers there, and that's 400 million years. So to grow by, say, a factor of 2 at Eddington rate, which is very large, that's quasar luminosity, it takes several tens of millions of years, and that's only a factor of 2. So if you want to grow from 100 solar masses, like a big star, to 10 to the 9 solar masses, that takes giga years. Or in redshift terms, if you start very early, redshifts less than 3. So how do we get so massive quasars seen by the James Webb telescopes so early? Well, various proposals have been made. Early formation of very massive stars collapse at very high rates directly into a central gas clump, which then forms a very dense cluster, which then runaway collapses to a big black hole. We don't know. We have to really understand this before we have the true answer. So these are our favorite ideas: heavy seeds, super Eddington accretion, low radiation efficiency, and enhanced tidal stellar disruption. So this is going to be one of the, very exciting fields of the future, is to actually, again, experimentally, not just by guessing, experimentally understand this evolution. Let me finish by tell you how we will go on. What do we do next? Well, there's so much to do, also beyond my own, lifetime. We are now looking at some stars with gravity, which seem to have an orbital period, not of 20 years, but only a few years, and come as close as 2030 AU. That's going to be enough to see the spin. Likewise, with spectroscopy, accurate spectroscopy, with the so-called ELT, 40-meter telescope of ESO, you might be able to see such high precision measurements of the line emission that we can get at the quadrupole and the rotation of the black hole. And finally, of course, if the EHT people will measure still more accurately, they can define the size of the photon orbit and the ring size very accurately. But then in the end, I put my bets on space interferometry, the LISA mission of ESA and probably also NASA, where you will have in-spirals of stellar black holes into supermassive black holes from time to time. And if you have one of those, it takes a long time, years, before the in-spiral is completed. And therefore, you can build up enormous signal-noise ratio and get to uncertainties in these parameters of 10 to minus 4. So this size concentration parameter I introduced initially can be truly nailed of whether or not it's 0. So that might be in about 25 years from now. So this field will continue to be extremely exciting, and it's at the core of physics. it surely also is highly interesting for astrophysics and how galaxies evolved and so forth. But I'm a physicist more at heart, and we don't understand yet the details of gravity theory on the smallest scales or the quantum scale. Thank you very much.
You're welcome. Well, let's first give a round of applause for the excellent presentation of Professor Reinhard Genzel. Okay, Professor, thank you very much. You see, from now, I mean, at this moment, 2 years ago, I don't think there was this claps and this also these figures that people now put in the presentation. So from them, you can imagine how they were pleased with your presentation. So I have some questions. Well, I mean, as I said, we have an audience in Federal University of Pará, but also we have people participating from other places in Brazil, and even abroad. So let me then start, if that's okay for you, with the first question mentioned here from Satish Kumar. From Unirio in Rio de Janeiro, Brazil. Satish, would you like to turn on your microphone and make your question, please?
Thank you very much, Luis. Once again, you are the lifeblood of Brazilian physics. And Luis organizes the excellent lecture series of any places, right? So thank you so much for this thing. Thank you, Dr. Genzel, for a great talk. I have three very simple questions. Firstly, in the beginning, when you talked about the various black hole solutions, you did not mention charged black holes, Reisner, Nosdam, or Kerr-Newman. So does the observational instinct say that charged black holes don't exist, or?
No. The answer most people in astrophysics will give you is, in contrast to charged black holes in theory, these black holes live in an environment which can carry charge through magnetic fields and everything else. So now imagine you had a substantially charged black hole. Immediately a current would flow to discharge it. So that's why, accepting a minutiae of a charge, most astrophysicists, when they make, say, calculations or observations, would assume that this discharging takes place, and therefore you can forget about the Meissner black hole.
Okay, got it. So another thing I found very interesting, especially coming from you, is like, okay, there is possibility, there is life for grav stars and fuzzballs and all this exotic physics. It's good encouragement. So is that based on the reason?
Yeah, look,
please go ahead. Yes.
I don't have any reason to apologize for that, but the thing is, I'm amazed, truly amazed, that the number of AstroPH, our preprint server, publications since the last 5 years, with some title having to do with black holes or general relativity or something like this, increases exponentially. So that tells you how extremely excited many theorists are. And I don't want to, at this point, be sort of the high priest who says, this is all nonsense. Yeah. I mean, okay, I'm going to tell you a joke now. Of course, a lot of people in the public asked me about wormholes, and because they would like to travel or something like this. And I say, look, I'm just a dumb experimentalist. I don't know much. But I've asked someone who does know, and that's Roger Penrose. And I've said to Roger, look, they always ask me about wormholes. What do you think about wormholes? He says, rubbish.
So, but is this like, is this because the size of the objects that you see are much larger, maybe many times larger than the event horizon of the possible compact object that exists inside? Is that why you say this possibility exists?
That which possibility exists?
It could be other than black hole. It could be grass.
Okay. Well, no, I mean, I think it's very clear that if you look in the literature, exactly it was when the first measurements of the galactic center were done with gas by Charlie Towns. Was one of his postdocs, very famous physicist. And we used gas motions on scales of several light years, okay? And so while we had evidence for mass concentration exactly of a few million solar masses, within a few light years, you can put an awful lot of stuff. And that's when, in fact, many of these ideas, like the boson star and the fermion ball and so forth, became very, very popular. That died out over time because the measurements got better and better. But Remo Ruffini and his group have revived that and shaped it up, and I want to be a good scientist to make sure, okay, well, then we deal with it. We're not just throwing it away.
Thank you so much for being so encouraging, right? Thank you so much. Thank you, Luis, once again.
Well, thank you, Satish, for your questions. So the next question comes again from Rio de Janeiro. So Professor Mauricio Calvão from Federal University of Rio de Janeiro. Mauricio, would you like to turn on your microphone and perform your question?
Yes. Okay, do you hear me okay?
Yes.
First, I would like to thank for the excellent presentation of Dr. Genzel. And my question is somehow related, perhaps, to one of Satish, and it deals with the distinguishability between really collapsed objects, such as the black hole, and and other objects such as a neutron stars. If we were only in the field without in unrealistic situation and the object isolated, I guess these observations could not distinguish between a small enough but greater radius than the Schwarzschild one and are really collapsed. It seems to me that we might have some better chance if we had binary mergers, because then I guess we would have a different behavior due to accretion disks and the light and matter as compared with the merging of two black holes. Well, could you, am I?
Yeah, well, okay, yeah, it's all the same to me. I mean, it seems to me whether you have a star moving around very close a black hole, whether you use the photons, whether you have gas, all of this gives you an aspect, as I showed, and every single one of them is open to criticism. There is no doubt about it. The gas, for instance, although it comes very close, remarkably close to the event horizon, so it's going to be difficult to in fact, I showed that how difficult it is to defend the fermion ball hypothesis. The counter opinion, of course, could be, no, wait a second, you haven't proven that this is virialized motion. Yeah, I mean, so indeed, it could be outflowing motion. We don't have that accuracy quite yet. In the case of the photons, you know, it's extremely difficult in the galactic center case to actually get an image like the one I've showed, because the source, the radio source, as Sergei saw, is highly variable. And that kills, or at least makes it extremely difficult to do good Fourier inversion of the UV data of the interferometer. So there are, you know, good experimental reasons why one has a right to question, especially the innermost measurements. The stellar measurements, I would say, look, don't try. That they are so good now. They will become better, but they're so good now. I wouldn't. But that's only 1,000 Schwarzschild radii. So we are really talking about those parts of the proof going still closer. Many people, of course, have been in the past using radiation phenomena, and still do. That's why I introduced this thing over through the active galactic nuclei. So people said, well, okay, there's X-ray emission, and the X-ray emission is variable. Therefore, you know, it has to be a black hole. That one, I would say, I'm with you. That's too weak. That I would not allow as an experiment, if you like. Okay. But there may be future measurements of more substantial nature. Even with X-rays, where then another one would be lensing, lensing of a star. That would be very, very good if you had a background star and then it has a path, and then you get a micro lensing effect. That would be pretty good. All of this should be tried. So I'm with you. You know, we should work hard. We should not go over the hill. But on the other hand, the fermion ball or boson star hypothesis hangs currently on a thread, because the classical way to introduce especially the fermion ball, is through dark matter, and that's what the Ruffini group correct. And that on cosmological scales. So they basically say what we're looking at is dark matter. And so dark matter, of course, you You want to explain now all of the black holes. Well, I'm sorry, if you have the galactic center and you want to have that explained with a fermion ball, then as I showed, the fermion has to have 500 kilo electron volt mass. That does not work for a quasar anymore. The quasar would collapse, okay? And so if you use other techniques of statistical nature, then some of these explanations may work for one object or another, but not for all of them. But nevertheless, we will work hard to see and test.
Okay. Thank you very much.
Thank you, Mauricio, for a question. Thank you, Professor Genzel, for your answer. We have some questions from people in the audience, but unfortunately, the sound there is not that good, so I will make the questions for them. So the first that I'll make comes from Professor Carlos Herdeiro from University of Aveiro in Portugal. He has written down, as your personal view, which type of experiment, interferometry, gravitational waves, orbit tracking, or others, do you think may be the most likely to find some surprises or new physics or deviations from GR, or even deviations from the Kerr hypothesis, the Kerr geometry?
Yeah. Okay, the answer. Look, as we speak, we keep making, right, and ever better and ever more precisely. So it's possible that as we push some new limit of accuracy, all of a sudden something doesn't add up, and that would be an option. The most likely situation is indeed gravitational waves. Remember, I said I put my money on the space mission LISA. I don't put it on the ground-based experiments, and I tell you why. Because of the seismic and audio noise on any ground-based experiment, and even if you go underground, you have to have a relatively high frequency experiment. And that only works for relatively low mass black holes. So if you're happy with that, I would say perfect. We will see with the further improvements of the ground-based observatories. Now we have 3 in Japan, in Europe, and in the US. We will see higher accuracy numbers. Now, the events are very rare and they cannot be redone, right? So this famous merger is also the best merger because it was very high mass and relatively close by. Many of the others, you would not be so impressed by the signal noise ratio. But then the extreme mass ratio in spiral seen in space with LISA has the advantage that there is no seismic noise, therefore you can go, or no vibrational noise, and therefore you can go to much lower frequency and therefore to much greater masses and much greater distances, rarer objects and more objects, and therefore your accuracy in principle can be fantastic. But I can give you a caveat right away. Exactly because of the rareness of the stellar black hole mergers, which can be seen by LIGO, you don't have to worry about anything disturbing you other than that. In the case of LISA will at the same time hear hundreds of such mergers. And so there's going to be, confusion noise due to all these different hums at different frequencies and different stages of info. So I want to see that, how our colleagues get that squared away in a statistically believable way that they can really interpret the data. But as I said, I think that's the most likely way. And also, by the way, it is so accurate in terms of getting so close to the photon orbit. Nothing else can go directly to the photon orbit, other than a merger, because as I showed you, the lensing experiment from EHT goes only to about twice the photon orbit. Yeah, then inside the light is gone. So it's really the inspirals go as close as you can really realistically hope to the event horizon.
Okay, thank you. Thank Carlos for the question. Thanks, Professor Genzel, for the answer. So we have another question from the audience. This comes from Juan Carlos Degollado Daza from UNAM in Mexico. He's presently here in Belém also. And he's asking, is there any chance to measure effects of dark matter at solar system scales using black holes, for instance?
So on solar system scales, yeah, okay. So the classic way to do this, and that's been done very, very well, I would say, is microlensing studies. And the world record holder is the Ogle experiment in Poland. And there's been a recent paper on this, which you might want to have a look at to see where they are. So if you look at that paper, you will then see that they have not seen for 25 years any long duration microlensing effect. And if you translate that into masses of a dark matter related black hole, say primordial black hole, then that excludes, say, half a solar mass, or even certainly one solar mass. So you only are left with the very small black holes which might have survived, and there is no signal noise ratio on that, and that's going to be very difficult to see. I mean, so the classical Hawking primordial black holes have a mass of 10 to minus 5, 10 to minus 6 solar masses. That's going to be very, very difficult to see. So you'd like to, have half a solar mass or something like something you wouldn't expect to be due to stellar evolution, but something which is big enough so that you can see the Einstein radius.
Okay, so thank you very much, Juan Carlos, for your question, and Professor Genzel for the answer. So, Professor, let me, in the AHT result, right, they first released the result of the MH87, then our own galaxy. In the case of stars orbiting the central galactic black hole, you have given us the conclusions of our own galaxy. Could you comment on the possibility of, do you think one day it would be possible to infer, such movements of bodies around central objects in M87 or other galaxies from, future technology or anything?
Absolutely. Luis, absolutely. Just would you give me a second life?
Well, I'll give you 100.
I'm having a lot of fun, but I'm afraid. So, yes, the answer is absolutely yes. And likewise, there was a question before, why not binary black holes? We're looking for them, okay? There's a whole shebang of microlensing people who are looking for binary effects, and we are in contact with them, so that if there is a binary black hole, say, relatively nearby, which we can resolve with gravity, we go at it. But the thing is, on the one hand, is it shouldn't be too far away, because then it's going to be very difficult to see the finer effects. And the other one, of course, is the resolution. To really see extremely high. For that, I would argue the best way then is in the difframetry experiment like gravity, only with 10 times the baseline. So then you have about 200 microarc-second resolution. That would be dandy. And then we could, for instance, easily do intermediate mass black holes in globular clusters, which is another thing we always wanted to do. But currently, if we do that, we will burn up. I mean, you have to understand, we are burning up per night 4 telescope, 8-meter telescope nights. So one night, effectively, in terms of money, costs $4 million. That gives you a feeling, okay? And so we can only do so many experiments, but the draw is full of them, and if others would want to join, absolutely. Unfortunately, is that, as I said in the very beginning, that optical near-infrared interferometry has been believed, with the exception of Michelson and Charlie Towns, by almost all people in optical astronomy to be non-workable. We have broken that barrier now by 1 million, but it will take a while to sink in. People in optical astronomy are more interested in big telescopes. And of course, we will get one in Chile in 3 years. We have built the first instrument for it too. But that's only a 38-meter telescope, only. Okay, so that's smaller in resolution than what we have already with gravity. So, I mean, there's all these things, where you can see what would you like to do. But certainly to measure a binary black hole in high accuracy, the motion of that would be fantastic. Yes, absolutely.
Okay, thank you. Look, Reinhard, so we still have some questions, but we are going like 20 minutes of questions and answering. Would you like to stop now, go a few more? What would you like to do?
I do have to cook tonight, so I'll give you another 10 minutes, okay?
Okay, let's work with that. So there's a funny question in the audience, maybe because they're seeing some frames behind you. They say, well, where's the Nobel medal? But let me tell you a story. So in 2011, came to Belém, Klaus von Klitzing, and he brought with him the Nobel medal, and then he left some people, even the students, to take pictures holding it with their hands. So it was really funny. So maybe it was motivated by this question. So let me now jump. There's yes, please. Oh, here it is. So let me make a print. Thank you.
No. It's pretty good, but it's all faked because it's a chocolate Nobel medal.
Yeah, I have one of these. Well, it's smaller, I should say. It's smaller, and I even brought when I visited.
Any one of you can get these in the Nobel Museum in Stockholm.
Yeah, I got one.
After our, 2020 was no celebration, but in 22 we had then a post celebration, okay, and of 3 years of Nobel laureates, and my wife bought about 500 of these, and I gave everyone in our institute a Nobel Prize.
Yeah, well, when I visited there, I also brought it and gave as a gift to the friends that stayed in Belém. But thank you for sharing that. So let me move then to the next question. So it comes from the young doctor João Paulo Brito, that is now a postdoc in Federal University of Pará. He has written down, recently we have passed by 2 milestones in the experimental studies of black holes, gravitational waves and the observation of shadows. Do you see another milestone ahead, or only improvements of those 2?
Oh, come on, Brito. That's unfair what you're doing. I would say there's absolutely no doubt that in theoretical limit, the EHT result is fantastic. But its true capability of revealing physics is modest, because you have to distinguish at essentially infinite resolution, which you don't have, the emission from the lensing and the photons going around from the basically distorted emission in the backside. So I would say at this point, other than the radius, which I said was a wonderful confirmation of the hypothesis, let's not overdo how much physics there is. Gravitational waves, I've said that already. Yes, I'm with you. But please keep in mind that the stellar measurements are pretty good. I mean, they are from a point of view of experimental quality, really. I mean, not bad for government work.
Okay, no. I mean, I think that he just forgot to write down, I mean, this, but I mean, he obviously meant that, and he's seeing something else that, I mean, it's not immediately in your minds, and maybe you could figure out. Maybe that's what he mentioned. So there's another question from one young doctor here, Haroldo Silas from he's in the audience, I think, but he is going to try to turn on his microphone. So please, Haroldo, go ahead.
Yes, I'm outside the auditorium now. Can you hear me?
Okay. Yes, please go ahead.
Okay. So thanks for the amazing talk, Professor Genzel. I have a question regarding the measurement of the spin of the black hole. Because in the middle of your presentation, you mentioned that we can infer the mass to be around millions of solar masses. What about the spin? Can we infer it also, or there is some technical experimental difficulty to measure spin instead of mass?
Yeah. So if you do a decomposition of the GR parameters of an orbital solution, then at the order of radius or periradius divided by Rg to squared, is it? You have the Schwarzschild precision. So that's what we have. But then the lens tearing precision, which gives you the spin, is one full order of magnitude in that term worse. And so that means in terms of numbers, the lens tearing position is about 50 to 80 times smaller than the Schwarzschild precision. The accuracy, the accuracy of the Schwarzschild precision at this point is 13 sigma. So divide 13 by 65 and immediately you see it. Not with that star. So the solution is either measure still better, and of course that has to be at Peri, right at Peri, okay, and that we would have to wait another 14 years, or another star, and that's what we're hoping for. And then I showed you at the end of the talk a star which might fit the bill. So we might have to be lucky, all kinds of luck here. The first luck is that Albert Einstein has given us this wonderful problem. The second luck is that when I started as a student, it wasn't solved yet experimentally, so I could, get onto it. And with Charlie Towns, I had the right mentor. The third luck was that exactly the kind of techniques which I learned in my life have helped. Not the only thing, but have helped to add to this. And then, of course, nature has given us these stars, highly elliptical orbits. It's so close to the black hole that they are, if they're a little off the mark, so to speak, they get disrupted. So how did that come about? I mean, we've not talked about this. How did these stars come in there? This is not easy to solve. I mean, so astrophysically, that was not expected, and would have had to write a proposal for the work in instrumentation. It would have been denied on the grounds that you can easily see from theoretical work that there can be no stars in this innermost region, at least bright stars, bright stars. Okay, well, all right, but they are there. So in that sense, we have to be lucky. So then you have to work hard, and you have to have a fantastic team. And I've always had a fantastic team. You can't do this by yourself, right? And
Okay, thank you, Haroldo. Thank you, Professor Genzel. So let's now move to a question that comes from a PhD student here from Federal University of Pará, Pedro Lucas Sá. He's asking, what challenges remain in observing and characterizing the regions close to a black hole, and how might future technologies overcome these limitations?
Right. Okay. So I mean, it's always the same sensitivity and resolution with all the experiments. Let's go to the EHT, since Dr. Brito was so extremely positive about the EHT. Well, I'm not. The reason I'm not is that in order to get the EHT to have, say, 3 times the resolution, which is really what you would like to have, you have to go outside in space. You can also go to shorter wavelengths, but that won't work because the Earth atmosphere at 500 gigahertz does not cooperate. So it's the solution, and everyone knows this, the true solution of a true performing machine is in space. These proposals have been submitted to both NASA and ESA already by the teams and have been turned down on the grounds of cost. I have to say, I'm sorry, we are in astronomy now hitting some of these, edges beyond which you cannot work. The particle physicists have to live with that too. So we have to live with that too. So that's why I'm pessimistic on the EHT side, and in particular in the galactic center, because as I mentioned, the source is variable. This is not true for M87, Louis. M87 is a much, much bigger black hole, but it's also exactly that much further away, so that its apparent size is the same size as the galactic center. But to then measure dynamical measurements, for instance, will take a very long time. I mean, there you were talking about weeks and weeks of telescope time. And again, the weather at 200 gigahertz, where the present EHT works, is not so cooperative. These people had one particularly good and fantastic run in 2017. That's where all the papers which are on the market really have come from. Since then, they have only had poor runs, or at least in the galactic center, runs which are not good enough. So that shows you that there are, just natural limits. If there would be more observing time in the galactic center, I could very well see that you make sort of a movie, and then you make a statistical subtraction of the variable part, and then you can dig deeper or something like this. But that is not possible.
Okay, thank you. So then a final question then, just to keep on the time that you said. So it comes from Gabriel Pacheco Ribeiro, also from the graduate program in physics of Federal University of Pará. He is asking, how accurate is the measurement of the mass, and to what extent does this affect the statistical significance of the result?
Okay, we currently are, in terms of purely statistical accuracy of the mass, at 0.1%, 0.1%. If you then take into account all kinds of known, systematic effects, which of course we are trying to improve on all the time, multiply that by, say, a factor of 2 to 3. So that's why I given this number of about 0.3% accuracy. For the Keck measurements, I'm afraid that's worse, because of course they only measure with one single 10-meter telescope. So there the numbers are not quite as good.
Okay, Reinhard, thank you very much. I mean, you've been extremely kind, giving us a half an hour of question and answers. And well, I mean, I'll ask everybody for a round of applause to Professor Reinhard Genzel for us to close this section. Thank you very much once again.
It was a pleasure.